rates of change in linear and quadratic functions. So for any linear function, the average rate of change over any length input value interval is constant. So this uses sort of sounds like complicated language. Any length input value interval. What are my input values typically? They're typically x's, right? Or they're definitely whatever the domain is. Sometimes they use a different letter, but those are your x's. So it doesn't matter what domain you're talking about. The rate of change is the same. So if I'm looking at a line, then it doesn't matter whether I find the slope from -1 up to +1. I could do this piece of the line. Or I could find the slope from 2 to 3. I could do this piece of the line. Or I could find the slope of every bit of that line that we can see there. I should get the same number every single time, right? Constant rate of change. We often think of this as the slope of the line. And we'll talk about the slope of the line because it doesn't change for a line, right? It's always the same. So, from a table, it tells us, the table above gives selected values of the function f of x. Explain why f is not linear. Okay, so one option would be to graph this and see if those make a line. But how could we do this without graphing? What do you think?
Well, like from 1 to 2 is like 4 and 7, and that doesn't really show.
Okay, so a lot of times whenever I have these are not increasing at a constant rate, right? I go from 1 to 2, that only goes up 1. But from 2 to 4, that goes up 2. And then from 4 to 8, that goes up 4. Now, that's okay. You could still have a linear function with that happening, but it depends on what the y values do. So my y values, or my f of x values over here, from 4 to 7, I go up 3. That means my slope right here would be my change in y over my change in x, which would be 3 over 1, which would just be 3, right? But where we run into an issue here is from 7 to 10, this goes up 3. So here, my slope would be still my change in y over change in x, and my change in y is 3, but what is my change in x between 2 and 4? It is 2. So 3/2 is my slope, not the same slope. So if you find the slope between any set of values on a line, you're supposed to get the same number. So if we find the slope anywhere and it doesn't match the slope somewhere else, then we are not looking at a linear function for this. So if we have to write this out in words, because this is something that you may be asked to do, there are a couple different approaches that you could take. Okay, so I'm gonna do both of them here because I think they're good for you to see. You could just straight go with finding the slope, right? So you could find slope on, I'm going to call it 1, 2. And you could just show that you got 7 minus 4 over 2 minus 1. And that gives you 3 over 1, which is 3. And you could find the slope on 2, 4. And you could do 10 minus 7 over 4 minus 2, which is 3 over 2. Since these slopes are not equal, f of x is not linear. Okay, so that would just be like a straight, you're showing why it can't be. All you got to do is show what we would call a counter example. It's like, here are two places, the slopes aren't the same, so this cannot be constant. Another option for this, if you have something that's linear, your output values should increase by the same amount when the input values increase by the same amount. But our input values are not increasing at the same amount, so our output values should not increase at the same by the same increments. So you could say something like this: the output values increase at a constant rate. But the input values do not. So this function cannot be linear. You wouldn't need to put both of these explanations. They're just two different routes you could take if you were asked to explain. Because whenever we get to, test time next week or the beginning of the next, there'll be, not a ton, but there'll be a few where you'll have to explain yourself on those. Okay, so our next example, we are supposed to consider the quadratic function g of x equals x squared and complete the table of values over the consecutive equal length input value intervals below. They love to use this phrase right here. Complete the table values over the consecutive equal length input value intervals. Now that is like a mouthful of words, but consecutive just means in a row, right? So you're not skipping numbers. If you're counting by twos, you're counting by twos the whole way, right? Equal length just means what it says. They're equal length. So if this interval is 2, the next one is 2, and the next one is 2. And then input values are typically your x's, but it could be a different letter, but it's going to be on the left side of the function, right? So we're going to complete these two tables that they have here for the consecutive interval of equal length input values, right? And can we all agree we have consecutive equal length input values? We're going up by 2 in between each one of these when we go to the next x value. So negative 3 squared is 9. Negative 1 squared is 1. 1 squared is 1. 3 squared is 9. 5 squared is 25, right? They gave us a pretty easy one to plug into. These are our input values. Now, this asks us for our average rate of change from negative 3 to negative 1. When I have a table, what I like to do for this is I just look at the change in the graph. So over here in this table, if I'm going from negative 3 to negative 1, that's right here, right? And that from negative 3 to negative 1, that is up 2, positive 2. And then I also want to look at what happened to my output values, to my g of x here. From 9 to 1, that went down 8. So if I want to do the slope here, I don't have to do the full slope formula, although you could if you wanted. I can just do change in y over change in x, and that will give me negative 8 divided by 2, which will give me negative 4. So my average rate of change would be negative 4. Now, again, it's perfectly okay to take those 2 points and do 1 minus 9 over negative 1 minus negative 3 and do slope formula. That's going to give you negative 8 over 2, which is negative 4 that way as well. You can do slope formula. This is a little quicker to look at the table. So, when I'm looking at the table, if I want to go from negative 1 to 1, over here from negative 1 to 1, that went up 2. In fact, we've already said this is going up by 2 every time, right? And if I want to know from here to here, 1 to 1, how much did I change there? None. That's a 0. So my slope would be 0 over 2. What is 0 divided by 2? Is 0. 2 divided by 0 would be undefined, right? Zeros can't be in the bottom, but it's okay if they're in the top. My next one here, I would get from 1 to 9 would be up 8. So my slope here would be changing y, which is 8, over changing x, which is 2. I would get positive 4. And then for the last one, oh gracious, we got 25 minus 9 is 16. And so the slope here would be 16 over 2, which would give us 8.
So is it linear or is it not? Well, I guess
Okay.
it's going up like this.
It is definitely not linear. For a couple reasons. Number one, it was x squared. X squared is not linear, right? So they gave us the equation here. We know that it is not linear. But if I'm doing this for a linear function, all of my slopes, so these were my slopes right here, right? These numbers, these are those slopes. If it's linear, all of them will be the same number. We'll have 2 for all of them, or you'll have 7 for all of them, or negative 1.5 for all of them. But you might have been hesitant to say, wait, is this linear? What was making you think that? This is linear, right? This is going up 4, up 4, up 4, right? So your rates of change are increasing here at a constant rate. It is a positive rate, so they're still increasing. But so your rates of change are changing in a linear fashion. So it says, what do you notice about the average rates of change over consecutive equal length input value interval values? And you can say the average rates of change increase by 4 every time the x value increases by 2. So a rate of change is linear. Now, this will happen every time on a quadratic function, even if it's a much more complicated quadratic function. So we did the most simple quadratic function we could possibly do in just x squared, right? But we could have 3x squared minus 27x plus 429. This would still be the same. The number would be different and probably more complicated, but it would still be increasing or decreasing at a constant rate. So, selected values of various functions are given in the tables below. For each table, determine if the function could be linear, quadratic, or neither. So, you just want to look at your rates of change here. So, if I look at A, I can tell this is going up by 1 right here on each side. So, this increases by 1. But then over here, my f of x value increases by 3. And then over here, my f of x value increases by 5. So these are my rates of change of f. Is this linear? This function f of x is not linear, because if it is linear, we will see the same number every time there. Well, if we're increasing by equal length values, we will see same number every time here. That's not happening, so this is not linear. One way I like to look at this is look at it as a second difference is one thing that you would call. So this is the rate of change of f. You could do the rate of change of the rate of change of f. So if I look at what's happening here, when I go from 1 to 3, that goes up by 2. And when I go from 3 to 5, that goes up by 2. That is linear, right? So if you do a second difference and you get the same numbers there, then this is quadratic. Okay, this is what it's going to look like whenever these are quadratic. So this is quadratic. I'm going to skip B for a second. What would make me want to skip B? Whereas C, I like better. I go from 2 to 5 right here. 1 to 2, 2 to 5, 5 to 10. Are these equal length, consecutive equal length input values? They are not. It can still be done, it's just harder to do it. So I'm going to skip B for a second. I'm going to go to C. Now, do I have consecutive equal length input values for C? I do. I'm going up by 2. So if you have consecutive equal length input values, you really don't have to find the slope. You can just look at what's happening to the y's. That's what I did over here. But for B, it's not going to work. We'll have to actually find the slope. So here, notice that I go up 2, up 1, and up 0. Is this linear? It's not linear. Those numbers are linear. 2, 1, 0 is linear. But if my function h of x is linear, then I will get the exact same number here. I'd have 2, 2, 2. They'll all be the same number here. But they are not. So it's not linear. H of x is not linear. However, so let me label this. This was rate of change of h. So if I do this again, if I do the rate of change of the rate of change of h, right? So if I do this a second time, from 2 to 1 goes down 1. From 1 to 0 goes down 1. Those numbers are the same. So this one is also quadratic. Now, for B, we're going to have to look at the slope for these because we do not have equal length input values, consecutive equal length input values here. So from 1 to 2, that goes up 1. And from 0 to 1, that goes up 1. So the slope would be change in y over change in x, 1 over 1, which just gives you 1. But for the next one from 2 to 5, that goes up 3. How much do we go up from 1 to 4? Also 3. Now, those numbers aren't the same, but the slope would be 3 over 3, which is also 1, right? Yeah. So up here we got 5. This goes up by 5. So slope would be 5 over 5, which would give us 1. This one would be linear. It doesn't look linear in the beginning because 1, 3, and 5 are not the same numbers, but if you consider that x is not changing at the same rate, that it is linear Okay? So, concavity. For concave up, the average rate of change over equal length input value intervals is blank for all small length intervals. So, whenever we are concave up, what is happening to our rate of change? Increasing. So, increasing goes here. So, with linear, you don't have concavity. We wouldn't think about that. If I look at A, is this going to be concave up or concave down? That's concave up because our rate of change is increasing, right? So this would be a happy face parabola. But over here for C, would that be concave up or concave down? That one is going to be concave down because if a function is concave down, the average rate of change over equal length input value intervals is decreasing. Thank you. Okay. All right. So this part asks us to look at concavity. So whenever we look at the equal length input values, first of all, for A, B, and C, do we have equal length input, consecutive equal length input values? For all three of them, they're all the same. All of these are going up by 0.1, up by 0.1, up by 0.1. So since they are all the same, we can ignore them. They would change our slope, but as far as just telling if it's quadratic, linear, or neither, and concavity, we don't have to worry about it so much. So here, 4 to 1, I go down 3. From 1 to negative 1, I go down 1. From negative 1 to negative 2, I go down 1.
I guess that would be down 2, right?
Oh, sorry, thank you. I was saying it did not look right. Okay, so this is my rate of change of K. All right, this is definitely not linear, right? Let's think of the rate of change of the rate of change of K. From negative 3 to negative 2, up 1. From negative 2 to negative 1, up 1. So this is going to be quadratic. They might all be, I can't remember. And is it going to be concave up or concave down? Concave up. Okay, for B, from 1 to 4, we go up 3. From 4 to 7, we go up 3. From 7 to 10, we go up 3. What does that tell us? Linear, so no concavity, because linear functions are straight lines. They are not curved. Okay, and for C, we've got 1 to 6 or 1 to 7 goes up 6. 7 to 11 goes up 4, and 11 to 13 goes up 2. That is my rate of change of P. All right, if I look at the rate of change of the rate of change of P, which a lot of times will be called the second difference here. From 6 to 4, that goes down 2. From 4 to 2, that goes down 2. So since I'm getting that same number there, you're going down 2 each time, on that rate of change. This is quadratic, concave up or concave down. Down. Okay, questions? All right, so your assignment is going to just be a worksheet that's got tables on it. The first 6 are going to ask you for linear, quadratic, or neither, and then the last 3 are going to ask you for concave. We didn't really have any examples that were neither for the linear or quadratic, but if you see a pattern where your second difference is not constant, then that would just be a neither situation. And we're out of here at 12:30, so it's like a minute or two earlier than I normally pack up, but we don't really have time to get started. You can look at it tomorrow. You can pack up if you would like.